So in this class today we are going to study the concept is called the superposition theorem. So this is also one kind of technique we are going to use to solve the any electrical network. So before going to see how this superposition theorem can be applied to calculate the any response in any branch by using this technique. So before that we need to understand what will be the statement of this superposition theorem. So in any linear network, any in any linear network, if it has more than one source, then the response in any branch can be calculated as the algebraic sum of the response caused by the individual sources alone while other sources are replaced by their internal resistance. So this is what the statement we need to understand here. So what I'm saying is, in any linear network, if it has more than one source, that sources may be voltage or current sources, then the response in any branch, the response can be calculated. It may be voltage or a current through the branch. The response, that is voltage or current through the branch, can be calculated as the algebraic sum of the responses caused by the individual sources while the other sources are replaced by their internal resistance. You have to take one note here. So before going to start, how could be the statement? Note is here, the internal resistance of the first point is the internal resistance of voltage source is 0. So this is what need to remember on point. If the internal resistance of the voltage source is 0, then your voltage source, this can be replaced with simply a short circuit, something like this. Simply a short circuit, because this internal resistance is 0 and my voltage source can be replaced with simply a short wire with the R is 0, R equal to 0. So this is what you need to remember. And in case of your current source, the internal resistance is infinite. Internal resistance is infinite. So your current source can be replaced with your open circuit. Your current source can be replaced with a open circuit, something like this. Open circuit, there is no current flow through, it is simply a open circuit. So this is what we need to understand, these 2 points, before going to start our theorem here. So your current source is replaced with this internal resistance, and internal resistance of your current source is infinite, so this can be open circuited, and your internal resistance of voltage source is 0. So the equivalent circuit for this voltage source can be taken as the short circuit of the shorted line. It is showing like this. So to go for the explanation, so by seeing the statement, we are a little bit confused to understand the statement. So in order to understand the statement, we need to go with a explanation here. So for this, what I'm going to take here is, I'm taking a very simple network which consists of the two sources like voltage source as well as my current source is there here, something like this. My current source and voltage source is there. Very simple network. I'm taking, this is V, and I'm taking this R1, and this is my R3, and this is my R2, and this is my current. So this is the network has been given to me, and I want to find what is the current is flowing through, what is the current flowing through this resistance IR2. So IR2 is the response I want to find in this network by using superposition theorem statement. So how my superposition theorem is going to be applicable? If you see, this is a linear network. So this is a linear network. So I can apply my superposition theorem in this network. So I want to find what is the response in R2, which is the response caused by the individual sources. So I want to do is just, suppose my voltage source is present and my current source is absent, then what is the current flowing through R2, plus my current source is present and my voltage source is absent, then what is my current flowing through R2. Those two response, if you add, that response is also equal to the response which is obtained in the R2 due to the both the sources. So that is what the your superposition theorem statement. So in order to understand this statement, what I'm going to take is, I'm going to take the step one is voltage source is alone is acting. Voltage is alone is acting, and I'm taking only voltage. So the remaining sources are replaced with their internal resistance. That is what the point which is made here, replaced by their internal resistance. So my voltage source is present here. So this could be my circuit now. Is coming like this, is coming like this, is coming like this. When come to only my voltage source acting alone, the remaining sources has to be replaced with their internal resistance. So what could be the internal resistance of this current source? It is could be a open circuit. It is a open circuit. I can simply take, this is the open circuit now. So open circuit. Now if you now find what is the response in R2, what is the response in R2 due to that voltage source. So that is what I need to find here. Now see here, it is a open circuit. As your circuit is open circuit, only current is circulating through this closed circuit here. So whatever the current is flowing here, same current is flowing through R2. So I can write what is IR2. I can take, this is the first current I am finding. I1 is the current which is found, or it is calculated due to the voltage source. Then this is nothing but V by R1 plus R2. So this is the first current. I1 is the current which is flowing in the R2, that response due to voltage source. So this is what the first response I got. Now the step 2, what I am going to do is, the step 2, I will only consider the current source, and remaining rest of the sources has to be replaced by their internal resistance. Now see here, only my current source is present here. Only my current source is present, and rest of the sources, whatever the sources we have, they has to be replaced with the internal resistance. Then what is the internal resistance of this voltage source? It could be a short circuit here. It is a completely a short circuit. So I can take a short line here, completely a short line here. And this is my current I is flowing here. So if you find the current direction markings here, so this is what the current direction is going like this, here and here. So whatever the current I is flowing, this current is now dividing in R1 and R2, but I need to find what is the current here. So I can take this is I2 current, then apply the voltage current division technique here. Apply the current division technique and find I2. I2 is the current which is flowing in the R2 due to this current source. So I2 I can calculate it by applying the current division technique here. I2 can be calculated the total current into that R1 by R1 plus R2. So this is the equation 1 and this is equation 2. Now if you see here, we have the two sources, one is current source and one is voltage source we have. So due to the voltage source, this is the I1 response is got in the R2. Due to this current source, I2 is the response we have got in the R2. So my total response in the R2 can be taken as algebraic sum of the responses which is acting on the R2 individual. So algebraic sum means if you add the equation 1 plus equation 2, so that is going to give the total sum of the total response in the my IR2, this R2 resistance. So if you add these two one, I can write I1 plus I2 is going to give the current in IR2. Current in IR2. Now add these two, so that is going to give your response. This is R1 plus R2 plus I into R1 by R1 plus R2. So this is what the response in your R2 resistance by applying your superposition theorem. So in order to understand more clear about this superposition theorem, so I am taking one simple numerical here to more clearly understand purpose. And for this, I just am taking one network, a typical network here, and for this, I want to find what is the current is flowing through the 20 ohm resistance. What is my current I is flowing here? I need to calculate by using the superposition theorem. So that is what I want to do here. So before going to do that, I have to see that how many number of the active sources are present. If you see here, with the two active sources are there. So one voltage source and current sources. So I will start with the first thing here. Though I will go with the step one. Step one here is only the 20-volt source is present. Only the 20-volt source is present and remaining sources are replaced with their internal resistances, and I will calculate what is the current is flowing through the 20 ohm resistor. So if you see the diagram for this, so this could be coming like this, it's coming like this, and where my current source has been open circuit now. It has been replaced with the internal resistance and it is become the open circuit. So this is what my network is looking like this. So here I want to find what is the current is flowing. So before going to find what is the current is flowing, what I'm going to do here is I will going to take the equivalent circuit of this. I will going to consider the equivalent circuit so that it will be very easy for me. So if you see, this is my current direction, this is my current direction, this is my current direction, this is my current direction. So these two are in series. So these two are in series. I can replace this with the 30 ohms, 30 ohms, 30 ohm resistor, and this 30 ohm is parallel with your 10 ohms. 10 ohms. Then this is going to give us the parallel combination is going to give this parallel combination is going to give 7.5 ohms. Now my circuit is comes like this. Now if you see here, so this could be my circuit coming like this. Okay, and this is what the 20 volts and my 5 ohm and my 7.5 ohm is there. Now I can find what is the current is flowing here. So that current can be coming from 20 by 5 plus 7.5 is equal to coming around 1.6 amperes. So this is what the current is flowing from this part. So I can take here Now see, so this is what my current is flowing, 1.6 amperes now. So this 1.6 amperes, if you see here, so in this and in this direction, this is my, if you assume this is the 30 ohm resistance, and in this and this in the 10 ohm and 30 ohm resistance, this current is going to be divided here. So whatever the current is flowing in 10 ohm is same as the 20 ohm. So if you add these two, that is going to give the 30 ohm resistor here. So if you want to find what is I1 by taking this current here, so I1 can be found as here. So the total current into this resistance 10 by the total resistance, that is 10 plus 30. So that is what you need. So this is, if you do this, this is going to give you 0.4 ampere. So this is the equation 1. So zero point 0.4 is the current which is flowing through your 20 ohm resistor due to the only the voltage source acting alone. Now go back and again go for the step 2 where my 4 ampere source is present. My ampere source is present. Then what could be the rest of the sources has been replaced by the internal resistances. So this is simply a short here. It is a very short circuit here, and this is my network could be like this. So this is my network now. Now come back and see. This is my network now, and 20 ohm, 10 ohm, 10 ohm, and 5 ohm. Now identify the current direction, so that this is my current direction going like this, like this, like this, like this. So if you identify here current directions, so I want to find the, assume this is A and B terminal. In between the AB terminal, I want to find what is the effective resistance, what is the equivalent resistance for this network. I need to find. So for this, these two are parallel. These two are parallel, 5 ohm and 10 ohm. And whatever the effective resistance, net resistance you are getting, that is has been added to your 10 ohm resistance. So if you do that one, so that is what you are going to get. And this is what the networks look like. This is my 20 ohm now, and this is my AB terminal. If it is like this, what is the net resistance now we are going to get? These two parallel plus whatever the plus this 10 ohm resistor. Do that. So this is 40 by 3 ohm we are going to get. Now I want to find what is current here. So this is, I can take I2 current in this 20 ohm resistance. So I2, now apply the current division technique here. Apply the current division technique. So I can write, so 4 into 40 by 3 by 20 plus 40 by 3. If you do this one, you are going to get 1.6 amperes. 1.6 is amperes. So I want to find what is the total current. I is nothing but the algebraic sum of the response acting by the individual sources alone, I1 plus I2. So I1 is equal to, I can take here, this is 0.4 plus 1.6. So it is, the direction is same direction, both the current is flowing due to the both the sources. I can take, this is what my 2 amperes is the current is flowing through my 20 ohm resistance. This is how I am going to applying a superposition theorem, and I find the current flowing through any branch. So after applying the superposition theorem, this is what the effective response we are getting through the 20 ohm resistor. So this is what we are applying the superposition theorem. So without applying the superposition theorem also, this problem can be solved by using your nodal analysis or mesh analysis here. So I will go with the nodal analysis and I will show you the response. I want to find what is the current is flowing through my 20 ohm resistance. That is what I want to see here. So for this I will going through a nodal analysis and I will do that one. So for this, what I'm going to do, first identify the nodes here. So this is one node and this is another node. I can take this is VA and suppose it is BE. So I will mark the current direction with respect to each node here. I am marking the current directions. Now, if you take the node 1, at node 1 apply the KCL. So I can write VA minus 20 by 5 plus VA by 10. Because this is a zero reference node, I am directly writing the equation here. VA minus VB by 10 equal to 0. So if you take the VA is common here, so this is 1 by 5 plus 1 by 10 plus 1 by 10 you are going to get, and this is what you are going to get for VB, 1 by 5 plus minus plus 1 by 10 equal to 0, equation 1. And go for the node 2 here, go for the node 2. Apply here again KVL, then it is VB minus VA by 10 plus VB by 20 plus. So this is what the current direction is coming, and opposite to this one I can take this is minus 4 ampere equal to 0. Or you can write here it is like, I can write this is minus VA by 10 plus VB 1 by 10 plus 1 by 20 equal to 4. Equation 1 and 2. Now solve these two equations. Solve these two equations so that we are going to get VA and VB. Solve the two unknown parameters, have the two equations. Solve these two equations. You will get the V and VB. Once you will get the VB, once you will get the VB here, this point, can you find what is I here? I is nothing but VB by 20 ohm. So this is going to come around 2 amperes. You just go through and check, verify this one, it will come the same answer which is got from using superposition theorem, and what the answer you are getting through that nodal analysis, both are the same. But the thing we need to understand here is, so whenever for a given network, which technique we are going to apply in a very simple manner, so that concept and that kind of knowledge you need to acquire from these different techniques. Then what are the limitations of the superposition theorem? Superposition theorem limitations. Theorem limitations. The first point you need to understand here, the limitation is this theorem is not applicable. Theorem is not applicable for power calculation. For power calculation, want to find any power in any branch, any branch element, so this theorem cannot be applied, because the reason is the power is the product of your voltage and current, or it can be going like something like I square R, or it is V square by R. If you see here, your voltage and current, it is a product, it is square, it is your power is coming as a square term, so this is going to give that non-linear operation. So due to this non-linear operation, you cannot apply the superposition theorem for calculation of the power. The second point, the limitation for the superposition theorem is this theorem is not applicable. This theorem not applicable for the non-linear circuit, applicable for non-linear circuits. So if the circuits has, so what is this non-linear circuit? If the circuit has your devices like diodes and transistors, if you have, then that circuits has the characteristics is called non-linear circuits. For them you cannot apply your superposition theorem. So these are the two limitations you need to remember while you are applying your superposition theorem. So with this we will conclude this session for today.